Alright, from what we've watched so far on the NOVA documentary on fractals, fractals exhibit quality called self-similarity. There are things that are proportional, obviously. If things are similar, they're proportional. But what defines fractals to a large degree is the idea of self-similarity. So what is that? Well, let's take a look at this Sierpinski gasket. You can see the general shape, and as you zoom in, you will continue seeing the same shape, but on smaller scales. And there's no limit to how far you can zoom in. Or here, the Fibonacci rows based on equilateral triangles. One iteration, two iterations, three iterations. And you can continue to see the same shape as you zoom out or zoom in on different scales. Another one, a fern. Let's look at something that occurs naturally. Now this is a fern fractal, but you get the idea of the similarity, the self-similarity that exists in fractals. This is a really cool one. It's called the Menger sponge. You begin with a cube and then divide each face of the cube into 9 squares, like a Rubik's Cube. And if you hollow out the middle cube in each direction, you'll have the beginnings of a Menger sponge. So check it out. Leftmost, we have the first iteration of a Menger sponge. You begin with a cube, and then you hollow out the middle square from every side. Second iteration, third iteration. So you can see the self-similarity in each iteration. What's pretty cool about this one is how fast the number of cubes grows. It grows by a factor of 20 each iteration. So in the first iteration, we have 1 cube. In this iteration, if it was solid, there would be 3 times 3 times 3, or 27 cubes. But there's 7 cubic units that are hollowed out. So we actually have 20 cubes in this picture. And for each of those 20 cubes, it gets hollowed out and restructured so that they each have 20 cubes, which means there'll be 400 here. And for this iteration, there will be 8,000 tiny cubes. In this next video, we'll take you out to the 6th iteration, where there are 64 million cubes. Check it out. Pretty awesome shape. You'd have to zoom in quite a bit to actually see the smallest of those 64 million cubes, but that's how many there would be. Primarily from this, though, we are talking about the nature of self-similarity in fractals, the answer to that test review question. The next big idea relating to these fractals was recursion. Recursion is a mathematical idea of taking what you have and performing some rule or function on it. And then when you're done performing that rule or function, you have a result. Recursion would say take that result and repeat the original process to the result. And that would be recursion. And doing it once would be 1 iteration of that recursion. Doing it twice would be 2 iterations, etc. We saw an example in the video where they started with a segment and they erased the middle third of that segment. And then constructed a little dome. The rule was wherever you see a segment, eliminate the middle third of it and construct a dome. There's one iteration. If we repeat that, everywhere where we see a segment, we'll erase the middle third. And construct this triangular dome. It doesn't take too long before we have a picture which is pretty complex in nature. And you also will recognize the self-similarity nature of this recursion process. Let's do it one more time for iteration number 3. And what we're constructing here is the Cope snowflake. Using recursion. All right, moving on. All right, the next idea on this unit test is data analysis. Recall that in data analysis, we should always make some kind of a graph to convey information. And then after we do that, we should describe numerically and with words 3 different traits that this data set has. One being, what is the general shape? Is it skewed left or right? Is it mound-shaped, symmetric? Are there any strong patterns or clusters or deviations from those patterns? What about the center? What are most values? What's a typical value? What's the mean? What's the median? And finally, what's the variation? How are those values spread out? And so the questions in this part of the review assignment will talk about these things. Let's begin with center. We are all pretty familiar with mean. Mean will be the sum of all the values divided by how many there are. And recall, we'll always let n be the number of values. So the mean is equal to, we've got 1,690, sum of 1,700, and there's 1, 2, 3, 4, 5. Therefore, our mean is 340. Okay, this next question says, without actually calculating the standard deviation, just using the concept of standard deviation, in a sentence or two, make the case for whether it might be closer to 75 or closer to 300. So what is the concept of standard deviation? Well, standard means a typical value a normal value or an average value. A deviation is a stray from the normal. If you deviate, you stray from a norm. So in mathematics, a deviation would be straying from the normal, which would be a distance away from the center, the mean. So deviation for a number is how far is it from above or below the mean. If it's above the mean, its deviation is positive. If it's below the mean, its deviation is negative. But just as a general concept, a standard deviation is a typical distance from the mean. So in this problem, our mean is 340. So as you look at these values, there are 5 individual values. What is a typical stray from the mean? Well, 200 is about 140 away from the mean. Its deviation would be a negative 140. 30 is 310 below the mean. So we have a deviation of 140 below the mean, 210 below the mean, 80's distance away from the mean is 260 below, 800, wow, that's 460 above the mean, and 590 is 250 above the mean. So we can see all these deviations, they're all more than 100. In fact, they're quite a bit more than 100. So as we revisit the question at hand, the typical deviation away from 340 is clearly not 75, but closer to 300. This problem was designed to get you thinking more about the concept of what standard deviation means. Because if you remember the formula looks pretty intimidating and complex. But really what it's measuring is the concept of what's a typical deviation from the mean. And here we can see it's pretty big, close to 300 or so. That will be the end of this video, and we'll take up where we left off in the next video.